Hello students, previously we have discussed the fixed bias collector to base bias circuit. Now we will discuss the self bias circuit. In the self bias circuit, it is also called as voltage divider bias circuit. It is also called as voltage divider bias circuit, or it is also called as emitter bias circuit. Emitter bias circuit. Okay, voltage divider or emitter bias circuit. Then the circuit will be just very less difference here. You can see, if you take a transistor here, okay, if you connect a resistance, base resistance like this will be the base resistance, this will be the collector resistance, this will be the collector voltage, means VCC, and this is the grounded. This is the fixed bias. Then collector to base bias means so this will be the collector resistance, this will be the base resistance. The current flowing through this part will be the IB plus IC. Then here the current flowing will be IC, here the current flowing will be IB, the current flowing through this part will be IE. Okay, here it will be IB. So this is the collector to base bias. But coming to this self bias circuit will be like this. You take a transistor, NPN transistor, all are NPN transistors. Here we have the collector resistance. Okay, here we also have the emitter resistance. Then a resistance branch connected in this way. Connected to what? The collector. Let us take this as what? R1 and R2. Connected to a common ground. This and this will be called common here. So this is the self bias circuit. Okay. So the current flowing will be here is, let us take here I1. What is the current flowing through this part will be? Let us take this as IB. Okay. Then what is the current flowing through this part will be IC plus IB. Then here will be IB. Sorry, this will be IC. Okay. So this VCC, if point number one will be, if this I1 is far more greater than the base current, if the current flowing through this branch current is far more greater than the base current, then R1 and R2 will effectively in series. Will be effectively in series. Then hence R1 and R2 forms the voltage divider rule. Voltage divider network. Okay, using the voltage divider network, what is the base voltage we can write here? Base voltage is equal to, because we have to find this voltage across this point. So VB is equal to what we can write here? total voltage into, so what is the voltage here? R2 divided by R1 plus R2, because this is the base voltage, right? So base voltage will be appearing across R2. So that implies, then what do you mean by, what is the value of VE? Emitter voltage will be nothing but, what is the current flowing through this part? This resistance is IC plus IB. So IC plus IB into RE. Hope this point is clear to everyone. This is not IC now, this is IE, because the current flowing through this part will be IE, no? IE plus IB. So this will be IE plus IB. So then R1 and R2 are selected in such a way that R1 and R2 are selected in such a way that the base voltage should always greater than the emitter voltage. Then only base voltage is more than the emitter voltage means then junction JE will be in forward bias. Then voltage at the collector is what is the voltage across the collector? Yes, voltage across the collector. Yes or no? This is the voltage across the collector. How to find the voltage across the collector? Is you can apply KVL in this loop. Let me change the ink here. You can apply the KVL in this loop. Then what is the value of this VC? VC is nothing but, or else you can even find minus VCC plus IC into RC. Plus VC is equal to 0. Then what we get here? VC is equal to VCC minus IC into RC. Okay. Then the collector voltage across the collector is VC is equal to what? VCC minus IC into RC. Okay. Let us consider this point. RC is selected in such a way, such that collector voltage is more than the base voltage. Means if VC greater than VB, then junction JC will be in reverse bias. So the self bias circuit can be simplified. In such a way that, so this self bias circuit can also be simplified in such a way. You can see this one. If this is the transistor NPN, so this will be the collector resistance, and this is the resistor divider network, voltage divider network. Okay, this will be R1, this will be R2. Okay, now here we have the collector voltage, here also we have the collector voltage. Yes or no? This collector voltage positive is given to this collector voltage is given positive. This negative is connected to what? Ground. This ground means these two are same. This forms the input loop. Okay, this forms the input loop. Now we also have the emitter resistance. This will be the another loop. Okay, if this is the positive, this will be negative. So this will be the input loop, this will be the input, and this will be the output. Okay, so how do we find the Thevenin's theorem? So let me write here, self bias circuit can be simplified by using, remember this form, by using Thevenin's theorem. By using Thevenin's theorem. Okay, how do we find the Thevenin's theorem? Thevenin's voltage. I want to find the voltage across it. This Thevenin's voltage is equal to, how do we find the Thevenin's voltage? This is the Thevenin's voltage. Thevenin's voltage is nothing but the base voltage. Okay, how do we find the Thevenin's voltage? Voltage at B is equal, voltage at R2 is equal to, total voltage is VCC into same resistance R2 divided by R1 plus R2. So this forms the Thevenin's voltage. In the same way, how do we find the Thevenin's resistance? Thevenin's resistance can be obtained by deactivating the sources. Then this R1 and R2 both are in parallel combination. Then that forms the R1 into R2 by R1 plus R2. Okay, hope this point is clear to everyone. For self-bias circuits, the stability factor will be, for self-bias circuits, stability factor S will be equal to 1 plus beta by 1 plus beta into RE by RB plus RE. Okay, so from this we can make one comment here. If the emitter resistance increases, if we increase the emitter resistance, or Thevenin's resistance, then what happens to the stability factor? If we increase this part, the denominator will increase. Denominator increases, the stability factor will be what? Reducing. So in self-bias circuit, stability of IC is because of RE. So in collector to base bias, the stability is due to the RC. Here, the stability is due to RE. In self-bias circuits, stability of the collector current or output current is because of the emitter resistance. Stability can also be understood by another way. So how we can understand the stability will be, IB is equal to what? Yes, Thevenin's voltage minus the VBE divided by R Thevenin plus RE minus IC into RE by R Thevenin plus RE. How do we apply this one? Again the same. You apply in this loop. This loop, no? Then you get the same answer. Then the value of IB will be obtained. Okay, now let us make some points here. If temperature increases, then the reverse saturation current will also increase. Due to the increase in the reverse saturation current, IC will also increase. Due to increase in IC, then what about this IB value will be decreases. Means IC into RE will also increases. IC into RE by RTH plus RE. This value will also increases. If this value increases, then this is a constant, no? Then IB value will reduce. Then IB value will be reducing. So due to the reduce in IB, definitely collector current will reduce. The increase in IC will decrease the IC. Okay. I hope this point is clear. Therefore self-bias circuits, self-bias and collector to bias circuits, self-bias and collector to base bias circuits are the examples of stabilization methods. Are the examples of stabilization method. Okay, hope you understand these points. Thank you.